a little bit of. I recorded the meeting. Literally recorded the meeting. This is not the place I click. Whatever. Okay. Anyways, so we have to do like basic introduction to neural networks to understand things before we get in here. So, what is convolutional neural networks? Convolutional neural network is a type of AI that is used for image recognition, right? Um, so this is where we do things like image processing. We apply like convolutional operations, um, slide over input data using things like filter kernels, per- perform mostly element-wise multiplications, summary result, and the rest of the things. So this is the place where we do things like edge detection, feature detection, a lot of things happens down here, detect patterns and the rest of the thing. Basically, it just has to do with like image detection and then video detection, um, which is more like multiple mapping of images, right? And then there's 2D computer vision, there's 3D computer vision, you know. So whatever thing you're going to learn here is the basics of anything you are going to see in the world today. Is the basics of ChatGPT being able to see, the basic of vision language models, the basic of facial recognition, is the basics of everything, is the basics of cat dog recognition, is the basics of fingerprint recognition. Whatever thing you're gonna see here, um, is the basics of those things. And after this, by Friday, we should now start like proper. We are gonna implement everything we learned today with TensorFlow, and then we'll build an image classifier, and that will be the beginning of our implementation phase where we implement everything we've been learning, and then from there build object detection, and the rest of the thing. Whatever thing you learn here is the basics of everything, whatever thing that you would ever come across in computer vision. So, computer vision uses what is called convolutional layers. These are convolution layers. Each of them have different operations they perform. Each of these layers have different operations that they perform. So this is a layer, right? This can be layers. This everything. These are all convolutional layers. They perform different operations, and then this is our fully connected layer. In this case, where we have something like a neural networks layer, activation, dense, our activation layer. Then we do some com- hyperparameter fine tuning, weight bias, whatever thing, and then we do it over and over again. So they use what is called convolution layer. So these layers apply convolution operation into input image using filters, kernel to detect features as age, texture, and more complex patterns. So um so convolutional layer basically is where we do things like age detection, feature extraction, max pooling, um, whatever they want to do happens here. Even things like converting the image to gray, manipulating the image, applying things like augmentation, everything happens here. Then after that, we now pass it here. Then this way, like we do our computation. Like this is what I taught you guys last week is down here. But everything I'm gonna learn today is down here. That's with like the computation layer. All right. So um so this way we perform a lot of things. We do everything here. So what are the key concepts that we are going to learn here? It's going to be filters. So filters are all kernels. They are like little matrices, like metrics like 2 by 2 matrix, 3 by 2 matrix, whatever thing that we use to perform to to run on images to perform different operations. All right, they help us to extract like features like age, in an image, doing a lot of things. And then we have strides. So let's say, for example, this is a kernel, right? So 2 by 2 kernel means like a 2 by 2 matrix like this. So this can be a matrix like this. Is a 2 by 2 matrix. So this 1 0, this 1 1. This is a 2 by 2 matrix. And then strides. We also talk about strides. So they are like steps. I'm going to take all these things one by one in today's session. So I'm just explaining. Stride is the steps in which the filters are being applied across the image or across the, yeah. And then we have padding. Padding is like we're applying things on top of the image, like we are trying to pad things, applying paddings to something. I'm also going to show you guys everything. And then we have activation function. I think you guys already know about activation function. Our allow networks to learn. The fully connected layer is everything connected together. So let's dive in. So what are kernels? So kernels are like small matrices that we apply, all right, for feature extraction. Very simple. So there are just some random set of numbers that are being chosen to do different type of operations. So let's say that I want to like check for an image and apply something like age detection on the image, like to be able to find age in the image, right? What I do is that I pick the image. So let's say this is an entire image, all right? Then I apply some kernel on it, some filters on the image. I apply some filters on the image. So you can either call it kernels or you can call it filters, but one of the most used word is always filters. So in this place, where is the filter? The filter is here. So this is a 3 by 3 filter with some random numbers. So we pick this number, we pick this filter, and then we apply it on top of our image. So let's say, for example, in this particular step, we pick this filter, we apply it to, for example, in this place, right? We apply this filter here, as you see. And once we apply the filter, we do some simple matrix manipulation, like adding the first number. So let's say in this scenario, for example, this is the filter, right? So this is a filter right here. This is a filter. Then this is an old image. This is an image, for example, right? So we pick this filter. This is what this is a 3 by 3 filter. We pick this filter, apply it on top of this image, on top of this place in this image. And what do? We just do some simple matrix manipulation. So in this particular scenario, don't worry, I'm just explaining, I'm going to show you guys where these things are being applied. All right. In this particular scenario, we are doing something like 9 times 0. This is 9 times 0 plus 9 times 4 times 2, right? So this is 4 times 2. This is this 4 here times this 2, all right, plus 1 times what times this 1, plus we keep on adding everything, this time this time this time this. Then after that, our output image becomes this. So you see, our output image becomes this. Our output, let's say pixel or whatever thing, becomes 16. So let's say we applied an image, we add an input image of 1, 2, 3, 4, 5 by 1, 2, 3, 4, 5. After performing whatever manipulation, whatever operation, which I'm going to introduce to you guys as we go on, after performing the operation, most of the times the image used to reduce in size. The output of the image used to reduce. But whatever operation we would perform is going to help us to either perform edges or to help us sharpen or to get more better context or more better part of the image. Now, what is called convolution? Convolution is um, convolution is basically this thing here. This is what is called convolution. In mathematics, is called multiplication. Multiplication. But In computer vision, we call it convolution operation. So you guys will call it multiplication operation or whatever thing. But in computer vision, we call it convolution operation. As simple as that. So each kernel is designed to detect specific feature which allows CNN to understand and interpret context of image. Value of kernel are learned during training processes using back propagation that update the kernel value to better detect important feature. This helps CNN to take. So these numbers right here are always learned, and also sometimes, for example, if I'm performing something like age detection, these numbers sometimes are always given. So instead of you like thinking too much about like values to use here, sometimes they're always given based on the operation you want to perform. All right. And you guys are going to see how to keep on going in this session. So what am I saying again? Filters are like small matrices. This can be a filter of 2 by 2, which would look something like this. This can be a filter of 3 by 3. But this thing is what helps us to perform features extraction. This thing is very, very important in computer vision. And feature extraction is just some simple multiplication, which we call convolution operations. So we pick this thing and then we do some multiplication on the image. So this is an image. We pick a particular section of this image, all right, and then we perform a convolution on it. We multiply and then get out another image, an output image, which would be a result of the convolution that we have performed here. So if you see, for example, this image I will put in is a 6 by 6 image, and then we apply a kernel, we apply a filter of 3 by 3, um, a 3 by 3 size filter on this image, and then perform some convolution operation, and our output image became 4 by 4, but with some different new pixel numbers or new pixel values or whatever. So along this session, I'm going to explain to you guys what we can do to make, because this is a big problem now. Because if you imagine we put a picture of 6 by 6 and then we're getting 4 by 4, the picture has reduced in width and height, it has reduced in dimension. Even if the apple may be brighter or whatever thing, but it has reduced. So this is what we call filters or kernels in computer vision. These are like things you need to understand at first. These are a pretty image. We have our filter. We apply our filter um, on our input image, and then we do what we get our output, a different our image, but with different dimension. All right. Okay. And then what is striped? So if you observe this video, this thing that is running around, you will see that this image, for example, once we apply this kernel size on this particular part of this image, because mind you, we are applying per section. All right. So let's say this is a 3 by 3, would apply on this particular section of this image, which is what, 3 by 3. If it was 2 by 2, we're going to apply somewhere around here. All right. Now, once we apply, we need to perform this entire operation on this whole image. So what do? We move one step ahead. So, for example, we move one step after we perform this operation. For example, in this place, perform one operation. We store the result here in a new, let's say, a new array. We store the results here and then we move one step. All right. So if you want to perform the operation faster, you want to like perform whatever thing faster, you can choose to move 2 steps. So instead of moving from here, all right, to here, we can choose to move from here to here. So we'll move after performing the operation, we'll move from here down to here. Now that step that we took is what we call strides. So if you move one step, one pixel away, that's called one stride. If you move 2 pixels away, that's called 2 strides. All right. So if you look at this, for example, we are moving one by one. Move one, move one, move one, we move one, we come down one. You see, we move one, we come down again. 1 here, we keep on coming, we come down here, down here. So this operation is called these steps we are taking is called strides. And in this scenario, we are taking just one stride. So that's what strides is. So stride in convolution is a process in convolutional neural networks where a filter moves across an input image by a set number of pixels at a time, known as a stride. Instead of moving just one pixel, a larger stride, a bigger stride means the filter skips pixel, which results in smaller outputs, output feature map, lower computational cost, and faster processing, but also risks losing a lot of details. Because, for example, if we are moving, can I delete that? Because, for example, shoot, okay. Because, for example, we are moving two steps. So um, let's say this is one step, all right? This one step. So we move from here to here. But if we are moving two steps, for example, we entirely skip like a whole one step and we move one step. We move like we leave one step, we leave the second step, and then we move to the second. We move two pixels away. We are going to lose features. We are going to lose details in the image because each of these things donate pixels. Each of these things means pixel, and with this, we are losing image quality. We are losing things in the image, and the AI will do wrong prediction. So the most strides you move, the more it will be faster because when you move more strides, we are going to perform more operations. But at this point, we are going to miss a lot of pixel. We're going to move a lot of, we're going to miss a lot of computational, a lot of, a lot of, a lot of details in the image. All right. So what did I tell you guys? So this is it. For example, this is one stride. So we move from here, we move one stride away. Our output become this and this. All right. Two strides. We move from one, we dodge an entire stride. So let's say dodge this entire pixel. So this pixel is missed. This pixel in this particular operation. The first operation we did, we missed two pixels. And then we moved down here, right? The second operation, we went down again. You see, we've lost 4 pixels already. But basically, that is what stride is for us. So in this example, if we take one stride, after performing this simple filter operation, all right, we are going to have a picture reduced from 6 pixels to 4 pixels, right? Which is exactly what is here, 6 by 6 to 4 by 4. When we move two strides away, still applying a 3 by 3 kernel filter, we move two strides away, our output is going to reduce to what? To just 2 by 2, which is not really good. But it depends on what you want to do and how fast you want your model to run. So, how do you find the output pixel size? It's a very simple mathematics computation. So, let's say we have n by n. Our n by n is a number of pixels by a number of pixels. So, let's say this is 1, 2, 3. This is 5 by 5, right? And then our filter size is 3 by 3. So the formula for it is just n minus f. This is this n here, right? Input image pixel minus f, which is the filter size, right? All over s. What is s? The stride. So let's say, for example, we're using two stride instead of one stride times n minus f all over s, which is stride plus one, also plus one. And that should give us the output filter size. But most of these things you're not going to need to do it, but I'm telling you guys these things so you guys understand what happens behind the scene. All right. Most of these things starting from Friday when we start implementing most of these things with TensorFlow, um, the those libraries already compute them for us. But this is how you're able to find out your output pixel. All right. This is how you're able to find out your output pixel. So to make you guys understand these things more, I need to jump to explain edge detection. So let's say I want to do what we did last time. Remember last time I showed you guys how to run to build an edge detection model. I remember telling you guys that most of these computer vision techniques, we don't necessarily need to use CNN to train them. We don't necessarily need to use like computer neural net. Sorry, not CNN, deep neural networks to train them. Most of them, we can just do like some little manipulation with mathematics, and then we can get it. So let's say, for example, we want to detect the age in this car. Like let's say this is the age. We want to detect the age. For example, we want to perform a vertical age detection in this car. We can just do simple. Let's say we pick a particular pixel, and then we say this pixel in this part of this image, we want to detect which place is the age here, the vertical edge. We can just do a simple convolution manipulation and then we'll solve it very fast. What do we do? Let's say this is the image, for example. Let's say this is the image and each of these numbers represent the pixel. I want to find the edge in the image. What we do is that we have a filter which was already given to us. This filter, this one we don't decide. This is a filter that is used for sober edge detection, this particular filter right here. There are a lot of filters out there you can go and do research about. There are a lot of other filters, right? But this is just a simple filter which has numbers 1 1 1 0 0 -1 -1 -1. We can use this, apply this filter to this image. So we pick this filter, all right, apply it to this image. So let's say this is, for example, we pick this place, we pick this filter, we put here, we calculate 3 times 1 plus, this is 3 times 1, all right, plus 1 times 1, plus 1 times 1 plus 0. Okay, these are actually some wrong numbers. Let me use this. So we have this 3 times 1, all right, plus 1 times 1 plus 2 times 1 right here. So if you can see this, plus 0 times 0, right? Plus 5 times 0, that's this. Plus 7 times 0, that's this, right? Plus 1 times -1, which is what you have here. Plus 8 times -1, which is here. Plus 8 times, plus 2 times -1, which is here. And you add all of this together, that should give us -5. And that automatically makes our new pixel. So our new image is not going to have this other pixel again. It's now having this new pixel value. And once we run this operation with one stride, what we mean is that after applying this whole thing here, after applying this whole convolution here, right, with this entire thing, we move one step. So when we move one step means I pick this whole convolution, apply it here. I apply it now on this one. Then I run it again. That will be 0 times 1 plus 5 times 1 plus 5 times 7. Sorry, plus 1 times 7 plus 1 times 0 plus 8 times 0 plus 2 times 0 plus 2 times 1. Now, whatever value that we have from this becomes the value that we have here. And then we keep on performing this until we move from year to year. We move from year to year. And then we move till we get to the end, and then we get these values. And then we move one stride under. We move one stride. We move one stride under, so we move down here, and then perform the same thing. Then the value comes here, comes here, comes here. Now, at that point, whatever output that we have here should definitely give us the vertical edge of this image. So should definitely like be able to draw out the vertical edge, or like a clear pixel of where the vertical edge is, and then blur out the rest of the place. So if you look at this, it's the same thing I just spoke about. So this computation, right, gives us this result, this result, this result. So let's say, for example, we have an image, all right. This is a colored image that I used here, all right, which I've not done justice to explaining well. But let's use a grayscale image so I explain to you guys very well. So this is a grayscale image of black and zeros. This black here, more numbers here, all right, means white. More numbers here means white, all right. Then 0 here means either means gray, and then -1. Let's say this image has like it had like -1 value somewhere, means black. All right, and then we want to perform want to find the vertical edge of this image. All right, we got a filter here, which is the correct filter used for vertical edge detection. You don't need to this one. You don't need to think about it. This is the correct thing used. So each of these donates something. So one here means one, which is one, which means white. Zero means gray, and then -1 means black. Want to apply this kernel on this image. So we'll be able to find on this particular image here, where is the edge. So we're going to pick this image, and then we want some computation on this image, all right, and we create a new image, and that new image should be like an image of that age, should be like an image with the age, like an image that, well, the only thing we are seeing is just the age, and then the rest of the things are not showing well. So what do? We perform our convolution operation on it, right? We perform our convolution operation on it. So once you pick this stripe, you pick this filter, you apply it on this place in this image. We do our convolutional multiplication. This time this plus this time this plus this time this, until we apply everything. This would give us our results. So if you apply, if you multiply this, would get our result to be like 0. All right, and then we keep on going. And mind you, our size of image will reduce, definitely it will reduce. So there's something you can do to make sure the image is balanced, right? And then you don't miss most quality, and then also you don't reduce the size of your image much. So once we apply all this, we pick this. So this right here is our small our our image. All right, we apply this, all right, with this, then the output would get to be something like this, which would be 0, 30, 30. And this is a more higher pixel value, a more white pixel in this middle. All right, and then zeros, zeros. So with this is where we have our edge. All right, and these are like the gray side. So this is just a simple edge detection algorithm that is just done without you doing training or whatever. We just do simple computation. We picked a grayscale image, and then we did a manipulation on it, multiply this, apply the stripes, move one step away, do the same operation again, move one step, do the same operation. Then our output image should definitely be an image that I'll be able to find the vertical edges in this car, in this image that we have here. So that's I had to explain that. I had to use that to explain where the stride, the kernel thing is being applied and how important it is. All right. Okay, so we can now go back. So that is stride, that's kernel. All right. And then we have something called padding. Now, remember, we have an image size of this. We have an image size of this. And then once we apply our filter on the image, the size of the image most times used to reduce to a 4 by 4 image. And that's a problem. So what do we do so that the image size doesn't reduce? What we do to make sure the image size doesn't reduce is what is called padding. So by padding, we can do something called zero padding. There's a lot of things you can do, but most common one is zero padding. That you pick one pixel of the image, one pixel around the image, and then you just pad it with numbers 0. Just apply zeros to that in the image. You just apply 0, 0, 0, 0 around it. Now with this, when we are performing our operations like edge detection or whatever thing that we are performing, we are now going to get a bigger pixel, a bigger image, number one, image without much lost quality. Because if you look at this, we've converted this image from a 6 by 6 to an 8 by 8 image, 8 by X pixel image, and we can still keep our operation, our previous size of image. Two, we're not going to lose details because, for example, let's say we had important image on this age, we had important details of the image on this age. Without performing this, and then we reduce the size of our image, we apply filters on it, we are going to lose some details. So padding is always very, very important. With this, we can perform a full operation. You see, we've added a full entire pixel on this image. By just padding with 0, 0, 0, 0, 0 all around the image, we can now perform a full operation on this pixel of this image, this center image, and we won't lose details. We'll still keep details as if we were still performing an operation in the middle of the image. But if you see, for example, we are performing an operation on this middle pixel, we won't lose any detail at all. Because with that, this pixel as is fully surrounded, and then we can perform any operation on it. But on a pixel like this place now, if we do our normal previous operation like this, we would we would lose details most times. All right. But because of pad it, we can now have like a full-fledged um pixels surrounding it, and then it becomes like the centered image, and then with that we do our operation and we won't lose details. So padding helps a lot. Padding helps a whole lot. It helps a whole lot. So padding in conclusion, is the process of adding extra pixels, most of the times, often zeros, to the border of an image before applying convolution filter. This technique has two main purposes. It prevents the output feature map from shrinking in size, that's the output image, with each convolution, because we're going to perform a lot of convolution. So let's say we would have a convolution that does things like edge detection, would have a convolution that does things like max pooling. Max pooling is like finding like the most important details in the image. Would have some convolution that does a lot of things. So without padding the image, and then we keep on performing convolution before we even get to the point where we have a fully connected layer. Before we get to the point where we have like our neural networks model to train, we have lost our image. So let's say we started our image with our image being 32 pixels. All right, and then we perform convolution. From what I've shown you guys, you know it is for sure that the image size will reduce. So before we are even done with the convolution, our image must have reduced from 32 to just 2 by 2, or from 32 to 16 by 16. With this image is now like it's garbage. Like we can't even, it's not even good for our training or whatever thing. So this is what helps us, right? It makes it that by each operation we perform, the image size doesn't reduce. We still maintain our image size and ensure that pixels at the edge of the input receive the same number of convolution operations as pixels in the center, preserving important information. I think I've explained that already. So now that's something called padding, all right? Stride, filters, padding. Now, another thing we do in computer vision is called max pooling. So let's say we have this image, for example. This image, for example, we want to get the most important details, the most important pixels in this image. Want to get like the most important pixel. One of the things we can do is to perform what is called max pooling. With max pooling, would apply would apply a filter on this image. Let's say, for example, a 2 by 2 filter, and then we get the most important or the biggest pixel. So for this example, the biggest pixel here is 5. So we create a new image, and then our new image will have what? 5. We move one stride. We perform that until we are done. With that, we have a picture, an image with a very, very good detail. There are a lot of pooling done. There's max pooling, there's minimum pooling, there's average pooling. So pooling layer using CNN to reduce the spatial dimension with an height of input feature while retaining the important features, important information. This involves sliding two-dimensional filter on each channel of the feature map and summarizing the feature within the region covered by the filter. So Even if we still reduce the size of the image, all right, we still keep the most important information. And that's why max pooling is applied. And max pooling is a very, very important operation in computer vision. Because even if we have a big picture coming, we still want to be able to reduce this image size and then still get big important details. So let's say this is an image, for example, is a full image, which is a 4 by 4 pixel image. We have this filter size of 2 by 2, right? We have a filter size of 2 by 2, and then we apply it on the image. So let's say we apply it on this part of the image, this part. Then we pick the pixel with the highest value. The pixel with the highest value here is 9. We pick that, then we store it in a new image, which is this. Our new image, our new image is going to be like this. First pixel will be 9. We perform that again on the second. We move one stride away, right? And then we perform it again, and then that should give us like 2. We move one stride below, all right? In this scenario, for example, we are moving 2 strides because as you can see, we have 9. We move 2 strides, we move stride 1, 2. We perform it here, and then we have 2. We move 2 strides below again. We dodge, we escape this first stride, right? We escape this first stride, we escape the second stride. We perform it on the next stride. We pick the highest value, which is 6. We store. We move 2 stride away. 1, 2. Move 2 stride away. We come in here. We pick this value 3, 2, 3, and the highest value is 3. We store it. With this, our dimension of our image has reduced from 4 by 4 to 2 by 2 drastically, but we still maintain the most important feature in this image. Or even if we want to move one stride away, so let's say we want to move one stride, the most important thing here is 9. So we have 9, we move one stride here. Then the biggest here is still 9. We move one stride, which is going to be here. The biggest is 2. We move one stride under. The biggest is 9. Move one stride, which is this. The biggest is 9. All right. So that's it. So, and then with that, we can still get the most important big, the most important values in our image. So most of the time, it's always use stride of 2. All right. It's always use stride of 2 with a filter of 2 by 2. So in this scenario, for example, we have our 10, 20, 8, 11. Move, we pick the biggest value to be 20. We move 2 stride, the biggest value is 80. We move 2 stride, the biggest value is 7. We move 2 stride, the biggest value is 11. All right. And then we get our new picture, which is going to be what? Is going to be what? 2 by 2 from a 4 by 4. See? So that is max, that's what's called max pooling. Max pooling gives us the big value, the most important part of the picture. There's also what's called minimum pooling. So in this scenario, you're picking like, for example, in this particular image, right? We are picking in max pooling, we pick the the biggest pixel, which is going to be in this scenario. The biggest pixel here is 3. 3. We move 2 straight away. The biggest pixel here is 4. Move 2 straight down. The biggest pixel here is 6. We move 2 straight right. The biggest pixel here is 5. Minimum pooling, we pick the least pixel, which is -1, 2, -1, and 0. Then there's what's called average pooling. So average pooling, what we do is that we pick this, let's say we apply 2 straight, right? So we apply a 2 by 2 filter, and then we find the average, simple average mathematics, and then the average we store it, and then we find another average we store, keep on moving that way. But most of the time, this one is always used most times. All right. Okay, before I continue, I'd like to check if you guys are hearing me. Can you guys hear me? Can you
Yes.
guys? All right. Okay. So I need you guys to understand this thing because they are very, very important in computer vision. I'm going to recap it. Filters, right? Filters, or kernel, right? They are simple metrics that we use to perform operations in computer vision. All right. And then stride is how many steps we take in performing those operations. Let's say we are performing something like edge detection or whatever thing. How many steps we take to perform these operations. And then padding, while performing operations on the image, while performing operations on the image would always, most of the time, lose its pixel. All right. With that, we want to make sure we maintain the pixel. What we do is we pad the image on 1 pixels by what? By 000. We pad 0 zeros, just 1 pixel. You can choose whatever thing you want to do. You can play around with it, do anything you want to do. And then max pooling that we are picking the most important parts of our image, of our picture out. And then the example which I explained with vertical edge detection. So we want to find the age of an image, for example. A very simple thing you can do just by getting a filter of an edge detection filter. We apply this filter on this image. So let's say this is a particular angle of the image, or this is a particular place in the image. Once we apply this filter, no matter what happens, once we apply the filter and perform our convolution operation, our result should be this, which vividly is going to be the age. If we print out this image, it's going to detect the age of the image. So now after everything that we've done, man, after everything that we've done, we're going to now form a fully connected layer. Um, so let's say, for example, we are trying to predict that this is an image of two. All right. So this now what where everything about computer vision comes in. So let's say I want to predict an image too. All right. So I want to train an AI model for what? For image or handwriting recognition. We pass in an image, but we cannot pass in an image as it is, because we need to do some operation. We need to like find some important things in the image. Like I want to find like age in the image. I want to like manipulate the image. I want to perform some convolution operation. Right. So what we do is that we have different convolutions that we want to perform on it. Right. So the first convolution is going to be what we do, like something like a kernel padding, right? So which um is going to be our first convolution. All right. After that, we perform max pool. So these are our first input. All right. Whatever thing that we've done in this place, our input image has reduced to what? 24 by 24 from 28 by 28. We perform max pooling to find the most important pictures, the most important features. So if you see, for example, in this image, some places in this image are not important. I want to discard them. I want to find like where do we have more black, where do we have like more pixels in this image, where do we have more details. We perform max pooling on it, and we apply a 2 by 2 kernel, 2 by 2 filter on it. And that reduces our image from 24 by 24 to what? To 28 to 12 by 12. And then we perform padding on this image, all right? And this reduces the image from, so let's say, for example, in this particular example, we are performing minimum padding, all right? We perform padding, um, sorry, what am I saying? In this example, we are moving from like 12 pixel, we perform max pooling, reduce the image, we pad this image a little bit, all right? And then we do a max pull again in this place. Then after everything, our image has reduced from 28 by 28 to 8 by 8. All right. And then we pass it through our last layer where we do like we flatten the image. All right. Now this place where we flatten the image is what you guys saw me do last week, where after like we pass in an image and then we have to flatten the image and send it to the neural networks model. At this point in the convolutional neural networks, we don't flatten the image yet. At this point, we don't flatten the image. We still have the image as it is. But to be able to pass it from here to the CNN, to the neural networks model, we need to flatten it and then pass it here, apply some activation functions, pass it here, apply some operations, our neural networks operation, and then we do a prediction. And after the prediction, we pick our output image and then we do the operation again. We do like gradient descents, we keep on performing the operation over and over again. So let me show you guys a simple CNN architecture. This one looks a bit crazy. Like we've lost a lot of details here. So I need to find ones where like at least we still have our image kept. I need to find one where we don't like lose everything. Okay, let me see this one. Uh-huh. So in this particular image, for example, um, so let's say these are CNN network, right? In this CNN network, we have first of all our input image is this girl here, and then we are performing some operation, some convolution. So we pick, let's say this particular pixel, all right, is this small corner that you're seeing here, all right? So this is the entire picture. We pass this picture, we perform a first operation, want to find feature, want to do feature mapping, right? Now, these are first convolution. And then after everything, we perform pulling. Can be max pulling, can be average pulling, can be minimum pulling. And then with that, our image size reduced. After performing from this feature mapped, right? So let's say we perform age detection here. We did age detection here. We perform pulling on the image. The image size reduced a bit. And then after performing pulling on the image, we performed another feature map here. Let's say we are mapping age or whatever they want to map again, or before this point we've applied maybe like padding, the image size increase, we perform a feature map and then we pull again, the image size reduce. Now while we are why are we pulling is because we are trying to get the most important details whilst we're performing convolution. Also we are still padding and running some operations. Everything right here is convolution operation all the way down here until we flatten our neural, until we flatten the image, right? And then we pass it to a neural networks model. And the neural networks model will now detect if this was Donald, Goffy, this was whatever person with whatever thing. So you see, we have a fully connected computer vision CNN model here. Perform feature extraction plus feature map. This is where we do our classification right here. Is where we do like detecting if this was a picture of whoever I want it to be. Let me show you guys another example. Um, Here's another example. For example, here's another example. We have our input image came in here, right? We perform. So let's say this is we just pick 36 by 36 pixel out of this image. We pass this image to our first convolution. Our first convolution was we perform, let's say for example we perform max pull in this image. The image, this pixel will reduce 28 by 28, right? We perform another thing, right? After performing max pulling, image reduced to 14, right? We do some convolution again, we find features, we do anything, the size reduced, and then we pass it to our last flatten layer, and then we move on. So this is what happens. This is exactly what happens. All right. Okay. Let me just explain this one. Our input, we perform pulling, pulling, pulling whatever condition, we have a flattened layer, and then we have a fully connected neural networks. We can choose amount of node, whatever you want, and that will now give us our output prediction. Then we perform it over and over. We train the model over and over and over and over and over and over again. So this is the bare minimum explanation of computer vision. So everything that we saw right there happens in this place before we get into like this part of the neural network. So let's say our CNN is somewhere here. We perform CNN here, then we pass our CNN operation results to our neural networks model, which I explained last week, right? And that is it still here. So we have our input image, perform convolution, perform pooling, we flatten, and then we have our neural networks here. So I decided to make this class a bit short because this is going to be like the last class on theory and fundamentals. And I really need you guys to understand this thing before we start coding. From Friday, we'll start implementing everything that we've learned from the first week till today. Then we'll start building things like object detection, object classification, and the rest of it. So I'd like you guys to ask a question. Any question you want to ask, I'd like you to ask before we end the class. Okay, yeah, go ahead.
Can you hear me, please?
Yeah.
Thank you very much. Thank you for the class. So, please, I have a question, and the question is this: from the explanation you gave just now, what you explained now, I don't understand. Like, I know that we have the input layer, the layer, then the output layer. So now my question is that all those the CNN, like, which layer are they? Like, which layer are we going to classify them into?
Okay.
They are not. Are they not part of the layers? I don't understand that.
So yeah, so I remember teaching you guys last week. Then I explained to you guys about like input layer, deep neural networks. Now, what I explained to you guys last week is called deep learning. So deep learning is what you saw right here. So we have our input layer, our hidden layer, and then we have our output layer. But when performing, if you see, for example, the thing we did last week, we just flattened the image and passing here. That worked, but that doesn't work in the real world. That was just a simple deep neural network that I did to classify one or two things. So what happens is that in the real world, before we pass an image, before we pass an image to this input, you discover that last week I told you guys about things like before we pass an image, we want to be able to find the age of the image. We want to find detect like the age of the image. We want to be able to find like important details to extract features in the image. True or false? Now, to do that thing, the right industry, the right factory, the place where most of those things are always done is called convolutional neural networks. That is the place where we perform most of those things. In this place, we don't do anything like deep learning, gradient descent, nothing like that happens here. What happens inside here is what is me finding things like finding like age in the image. So I'm trying to pass in an image, but I want to create a new image which has different. I want to create a new image with with things like with important features. I don't just want to pass in the image like that to the neural. This way we have neural networks. But before neural networks, we have what? We have convolutional neural networks. If you want to do computer vision. So it's in this convolutional neural networks place that we do things like age detection. We try to find the most important part in the image. We do a lot of things. We do like a lot of feature extraction. We try to extract features. Those things you saw me do last week, those things you saw me do like carnal age detection, so whatever thing, and then you guys saw me detect age. This is what happens behind the scene. It is this thing that you see right here, this thing that you see right here is what happens behind the scene. This output image from here is what that we pass is what we pass in here. So after we perform that edge, we pass in here to like get the important features. We perform the edge again. At this point, we are trying to like get most important feature while still reducing the image quality. So we have this image coming like 224 by 24, but want to like get important features in the image and flatten the image. And we have like, although we have a reduced quality of the image, a reduced size of the image, we still have like very, very important features, and then we pass the image towards to our neural network model. So what does convolutional neural networks do? It helps us perform some crazy manipulation on an image that can help us to extract or get important features of an image while still maintaining the image, right? Um whilst you giving us our image, and then we use that to train our neural networks model, which is here. Now in this place is a different ball game. This place we can have a neural networks with like 300,000 parameters, 300,000 neurons. Let me show you, for example, YOLO architecture. So you understand what I'm saying? YOLO CNN. Look, you see, this is YOLO. This is what YOLO does. It performs all these operations. We have our first convolution layer, max, you see, we have our max pooling layer, all right? We have max pooling layer, we have they perform a lot of things down here before we get our flattening layer, and then we perform whatever thing where I'm looking for. Uh-huh. This is our CNN, for example. Wait, let me check YOLO. Okay, you look only once. So you see, this is YOLO. First of all, we do like convolutional neural networks here to extract important features in this image. And then after that, we now put it to a neural networks model, which can have like 200, 300 neurons, 400 neurons, 500 hidden layers, deep neural network layers. And then we do our prediction. If our prediction is not correct, we now run the thing over again. You see what I'm saying? So this is a different ball game, which is outside of, we put two of them together. We do our convolution, our convolution, and then we add it with a deep learning algorithm, and that's what forms computer vision. You understand me? That's basically what forms computer vision. So that's just the basic truth. We have our image, we perform feature map, we map the image, we perform another feature map, we flatten the image, and then we have our output. And then we use that to train, and then the model learns, and we pass the thing over and over and over and over and over again. Do you understand?
Yes, I understand. Thank you.
All right, Victor.
Good evening. Thank you very much for the lecture. So I just wanted to ask if you could help us with the materials for last class and this class. The
Yes. I'm going to even give you guys where I get the materials from. So I get it from this guy, Andrew Ng. Andrew Ng, deep learning. This is where I get the materials from. I'd like you guys to go and watch it. I'm going to drop an assignment today, and then I'm expecting it to be submitted on Friday. Okay, this is where I get the materials from. Let me see if I can share. This thing we are seeing right here is the age, the breeding age of everything. Like everything you're seeing in computer vision. No matter what people are doing, no matter how they are busy jumping around with ChatGPT and the rest of everything still falls back to these fundamentals. And if you can understand it, it will be really, really helpful for you as a person. All right, this is the YouTube session. This is the YouTube tutorial. This is what I used to learn computer vision like some years back. All right, let me share the session link too. Do you guys have the link for last class? The slide.
No, we don't.
I shared it. I shared it. I
You
shared the
can
slide.
you can share it again.
This okay, let me reshare it. I shared it the first day. I remember I shared it the first day. This was the time in Nigeria. Hello?
9:13.
It's 9:13.
Okay, I have a call by 11 p.m. Nigerian time.